we're going to talk about rational functions. A rational function, as we've talked about before, is a ratio of polynomials. So the main difference is we've been talking about just strictly polynomials. Now we'll be looking at a ratio of polynomials, which means that there's going to be a polynomial in the numerator and there's also going to be a polynomial in the denominator. That's going to be different than what you've seen before because now you're definitely going to be looking at a fraction. So I will ask you first to find the domain. I'm actually going to highlight this box or circle it at least so you know this part is super important that we do first. So you do this before you reduce anything. You have to use the original equation for this. To determine your domain, you're going to factor your denominator first, because all of the things that we're going to look at now that are rational functions will have a fraction and thus have a denominator. And we have to figure out when your denominator will equal to 0. That's going to be the restrictions on your domain. So I'll set each factor in the denominator equal to 0. Equal to 0. Again, this one has got to be the first thing that you do no matter what. You have to use the original equation. So I'm going to write a little star, use original equation. I'll tell you why in a little bit, / you'll see it through some examples, but this is important that you write a little note to yourself. So this is use original equation. Second one is, this might happen, it might not. It depends on the equation I give to you, but it says rational function is reduced if there are no common factors between the numerator and denominator. So sometimes you'll factor something on the numerator and then you'll factor something in the denominator and then you'll see something can cancel out. If that is the case, then you can cancel it out and then you'll reduce it. But if you can't cancel anything out, then your original function would be considered reduced. So if there are no common factors in the numerator and denominator. So the graphs that we're going to deal with in this unit might actually have something called a hole in it. A hole is basically, you've got some graph looks like this. Maybe I did one of these, but it like just skips a total spot like that. That's literally called a hole because it just like skips over one spot, but then it continues as if it didn't skip over a spot before. So a hole will occur only when you have canceled something out. So I'll say when you've canceled out a factor. So for instance, if you canceled out like x minus 3 from the numerator and denominator, that means you'll have a hole at x equals 3. So we'll kind of talk about how you find out the coordinates of your holes, but I just want you to know if there's something that you can cancel out, then I want to make sure you know it is truly from, that's where you're going to have a hole. Sorry, I just misspelled canceled. Okay, so let's go to the y-intercepts, just like what we had talked about before. To find the y-intercepts of a function, that's going to be like 0, comma something, 0, comma y. So you'll substitute x in, 0 in for x, excuse me. Okay, and then you'll find a value. Usually this will give you a point, and it'll be something that you can actually plot on your graph. For x-intercepts, there's kind of a trick to this one. It has to do with you trying to find out, again, as when x comma 0. So you're trying to substitute y equals 0. You'll notice quickly as we're going through this that when you use the reduced equation, you substitute y equals 0. A shortcut is to set the numerator equal to 0. So I'll kind of show you through an example. Set numerator equal to 0. The asymptotes, this one is a very convoluted thing. It says see the back. There are multiple types of asymptotes. If you look at the back of your worksheet, Here are all the different kinds of asymptotes you could expect. Vertical asymptotes is one, and then the other option would be either horizontal or oblique. So horizontal meaning just like a straight line going horizontal. Oblique meaning crooked. It could be like this. It could be like this. And then vertical, I'll draw an example of a vertical line over here. When you're trying to figure out your vertical asymptotes, that is truly from when you set your denominator of your function, let's say r of x, in lowest terms equal to 0, which means on this side you must use the reduced function. I'm going to write that down here, so make sure you write that too. That is, if you can reduce something out, like cancel out a factor, you have to reduce it out first before you determine what kind of asymptotes you have. So then, again, you're going to set your denominator of r of x in lowest terms equal to 0. It's going to give you certain x values. Those are going to give you your vertical asymptotes. For the other ones, horizontal and oblique asymptotes, this is going to be a little bit more complicated, but we'll do some examples of it. So it says find the degree of your numerator and then also find the degree of your denominator. You'll have three different choices about those degrees. Either your degrees are going to be different, where the degree of your numerator is smaller than the degree of your denominator. If that is the case, for example, if I had like x over x plus 1, x minus 2. See how the degree of this one is 1 on the numerator, and then the degree of the denominator is 2. So this is an example where your degree of your numerator is smaller than the degree of denominator. That would then make you go down this branch and you'd say, oh, I have a horizontal asymptote. It's at y equals 0. This is actually where the x-axis is. Now, if you happen to have a degree the same, let's pretend it's like x over and then x plus 1. Degree of your numerator is 1. Your degree of your denominator is also 1. If that's the case, then you're going to have a horizontal asymptote again, but you're going to take the leading coefficient of your numerator divided by the leading coefficient of your numerator. I'm sorry, did I say that opposite? I meant leading coefficient of your numerator over leading coefficient of your denominator. Again, we'll do some examples of this. It basically means it doesn't have to be y equals 0. It could be y equals 3. It could be y equals 5. This should just be a number. It shouldn't have an x in it. Last option would be if the degree of your numerator is greater than the degree of your denominator. This is when you have to do long division. I'm going to write that down. Okay, so you have to long divide. It's basically when you have, let's say you have an x squared on the top, you have an x on the bottom, you can actually long divide it. Your quotient has to be linear for your oblique asymptote to actually exist, which those will be the only examples that we'll actually do in class. So that would be the asymptotes on the back, very complicated. You're going to need to look at that flow chart pretty often and keep using it until you start getting used to it and figure out which one yields what. Last thing we have to talk about is when the graph of a rational function actually crosses an asymptote. Now, notice it will not cross a vertical asymptote. I'm going to write a little note. Doesn't cross vertical asymptotes. That's actually impossible. But the horizontal asymptotes and the oblique asymptotes are kind of weird in a sense that your graph will actually possibly cross it. I can't tell you just from looking at an equation if it's going to. You have to kind of solve for it and see whether or not it does. Set your horizontal asymptote or oblique asymptote equal to your function. I'll say r of x, our rational function, and solve for x. So if you don't have an answer from solving for x, that means it doesn't actually have what we call a cross point. If you do solve for x and you get something out of there, then it has a cross point. So this is going to vary depending on the equation that you're looking at.